Many of the islands of Arctic Canada are formed of limestone deposited in a warm subtropical sea about 400 million years ago. And if one goes to the opposite pole of the Earth, to Antarctica, it's possible there to find coal seams, not deposited under tropical conditions, but certainly under very much warmer conditions than Antarctica has at the present time. Now, you know from your knowledge of plate tectonics how those seeming anomalies can be explained. The continents have moved. They've moved as passengers on the rafts, which are the plates of the surface shell of the Earth. But the idea that the continents had moved was one which was very difficult for scientists to accept. And the difficulties that they had were often associated with the lack of enough evidence to support the theory. It isn't any good just having one piece of evidence to support a theory. You must have evidence from many quarters, and it must all be convincing. For example, the equivalent of earthquakes on the moon, that we call moonquakes, travel with a velocity through the moon of about just over 1.2 to 1.7, nearly 2 kilometers per second through that rock. A piece of cheddar cheese would transmit those moonquakes at just the same velocity, about 1.5 kilometers per second. So from that observation, that single observation, it would be possible to conclude that the moon was made of cheddar cheese. And of course we know it isn't. It's ludicrous. But it is supported by that one piece of scientific evidence. So when you look at the following hour, and particularly at the first half hour, which is the Planet of Man program, Beyond a Doubt Revolution, remember that you're looking with hindsight, and that the scientists of that time were simply exercising the skepticism which keeps science progressing.
There's just been a real revolution in the earth sciences. It follows a traditional pattern that has occurred in other sciences. In this case, the great concept has been that the continents can move about and are not fixed. And the experience in the other sciences has been that when such a change in ideas occurs, immediately after that, there's a great opportunity for advance. Many lesser things become clear. And so we feel that there will be a very great advance in the earth sciences during the next few decades.
The minuet is a stately dance for nobility. Encumbered by their extravagant costumes, the couple moves in a stilted fashion. Elegance gives way to awkwardness until the dancers are entirely out of step with the times. Revolutions are violent upheavals that rupture ties with tradition. Members of the establishment invariably muster to counteract such canons of change, but are eventually destroyed when the force of popular opinion sides with the revolutionaries. Revolutionaries bring about a major shift in the way man perceives himself. New slogans emerge. Old dogmas tumble. The king is dead. Long live the revolution. Yet, who is to check the power of the citizen who believes in long laws and short lives? The Epic of Man is a chronicle of revolutionaries who stood by to provide new solutions. The history of science is also the drama of revolutions, passionately fought by radicals who defied authority to expand knowledge, who turned their world upside down. the creative scientist deals with problems of cosmic proportions. The conversion of the mind of man. But man does not readily grasp new notions. He fixes on old concepts, basic images, and simple forms. The heavenly bodies hint of the divine form, circularity. Even the window to the soul is so shaped. The circle. It has no beginning, no end. It embraces perfection. Its regularity is comforting. In the 5th century before Christ, Plato propounded the notion of perfect form and bound scientific inquiry in a straitjacket for 2,000 years.
Those lovely patterns in the heavens are decorations in the visible world, but they fall short of those which are true. The true forms, I tell you, can be apprehended by reason and thought, but not by sight. Pursue problems in astronomy as we do in geometry, and leave the starry heavens alone.
By reasoning before the fact, the individual arrives at truth. The world is corrupt. Change is an illusion. All true motion must be uniform and circular. 500 years later, Ptolemy, looking at the night sky, is spellbound more by Plato than by what he himself observes.
We believe that the object which the astronomer must strive to achieve is this: to demonstrate that all the phenomena in the sky are produced by uniform and circular motions.
Yet he had observed that the motion of some of the planets, unlike the stars, was zigzag. At times, Mars stands still in the sky, reverses direction, and then pursues its former course. But the arbitrary law of uniform motion and perfect circles must be preserved. Ptolemy begins his model of the universe with a series of Earth-centered planetary circles. On the circumference of the large circles, he places smaller rotating circles. And behold, the divine Ferris wheel. A combination of perfect circles that will keep man entranced for another 1,500 years. By the end of the 15th century, the Ptolemaic model began to creak, but not with the rust of observable fact. Copernicus was even more enchanted with uniform circular motion than Ptolemy. The Ptolemaic system, while saving circular motion, did not quite maintain uniform speed.
Having become aware of the defects, I often considered whether there could perhaps be found a more reasonable arrangement of circles, in which everything would move uniformly about its proper center, as the rule of absolute motion requires.
In the 16th century, a revolutionary was born, who before he dismantled the models of Ptolemy and Copernicus, would state,
"Oh, for a supply of tears, that I may weep over the pathetic diligence of one who, relying on Ptolemy, wasted his valuable time and ingenuity in the construction of spirals and loops in order to represent that which exists only in the mind."
The times are ripe for Johann Kepler. Precise data on planetary motion is being collected, and the Copernican model does not accurately predict the position of the planets. After a false start in trying to unlock the secret of the orbit of Mars, Kepler discovers that his model is inexact by a small time margin.
If I had believed that one could ignore these minutes, I would have patched up my hypotheses.
Following 6 years of struggle with mathematical computations, he discovers that the orbit of Mars is elliptic. The key to planetary motion was a cosmic egg, not a perfect circle. Because Kepler chose to abandon conventional thought and stuck with stubborn facts, he broke a 2,000-year trance. But if the Earth moves about the sun, as Kepler had now proven, and is not the center of the universe, mankind yearned for a new form of stability. He turned from gazing at the stars to gaping at the ground itself for the security that some part of his universe was steady and unchanging. Even today, our cliches portray this common sense feeling. Keep both feet firmly on the ground. Until the early 20th century, geophysicists asserted that the oceans and continents were permanent features on the surface of the Earth. They conceded that the land rose and fell, but always in a series of uniform cycles. The Earth was a steady state machine, ever maintaining a harmonic balance between sea and land. This doctrine, known as Uniformitarianism, had the ring of Plato. As long as geologists chiseled at hard rock and studied the minute features of the Earth, the impression of a solid Earth would remain imprinted in their minds. But now, what profound notion was this unique man entertaining? It may have been this rifting and shearing that led him to shatter the established view of a rigid Earth, as Kepler before him. As a student of meteorology in Berlin, Alfred Wegener had devoted long hours to physical conditioning in preparation for his expeditions to Greenland. Little did he realize then that he would have to draw upon this reserve of strength to endure the rage of the scientific establishment which he would soon provoke. In 1915, he published a radical book in which he contended that the continents were drifting like pieces of a cracked ice floe.
The concept of continental drift first came to me as far back as 1910, when, considering the map of the world under the direct impression produced by the coastlines on either side of the Atlantic. At first, I did not pay attention to the idea because I regarded it as impossible.
According to associates, he had mentioned the idea much earlier. In modesty, he attributes the illumination to accident, but fortune favors the prepared mind.
In the fall of 1911, I came quite accidentally upon a synoptic report in which I learned for the first time of paleontological evidence for a former land bridge between Brazil and Africa. As a result, I undertook a cursory examination of relevant research in the field of geology and paleontology, and this provided immediately such weighty corroboration that a conviction of the fundamental soundness of the idea took root in my mind. It is just as if we were to refit the torn pieces of a newspaper by matching their edges and then check whether the lines of print run smoothly across. If they do, there's nothing left but to conclude that the pieces were in fact joined in this way. Let us assume that we can bet 10 to 1 of the correctness of drift theory just on the first line alone. The folding of the Sierras of Buenos Aires and the Cape Mountains. Then, since there are at least 6 independent tests available, we can bet 1,000,000 to 1 on the theory being right.
About 200 million years ago, he concludes, a supercontinent, Pangaea, began to break up, and continental pieces drifted to their present positions.
We may assume one thing as certain. The forces which displace continents are the same as those which produce great fold mountain ranges. Continental drifts, faults, earthquakes, volcanoes, polar wanderings are undoubtedly connected causally on a grand scale. However, what is cause and what effect, only the future will unveil.
A year after the 1922 edition of his book is published, the Royal Geographical Society meet to consider Wegener's hypothesis. The high priests of science convene to suppress heresy.
In examining ideas so novel as those of Wegener, a moving continent is as strange to us as a moving earth was to our ancestors, and we may be as prejudiced as they were. It is not easy to avoid bias. Whatever his own attitude may have been originally, in his book he is not seeking the truth.
Wegener has come forward with a theory which deals with the distribution of the continents in a bold way and offers himself for sacrifice. He is certainly getting it.
3 years later, the American Association of Petroleum a symposium on the drift theory, at which Wegener himself is present.
If we are to believe Wegener's hypothesis, we must forget everything which has been learned in the last 70 years and start all over again.
My principal objection to Wegener's hypothesis rests on the author's method. This, in my opinion, is not scientific, but is a selective search through the literature for corroborative evidence, ending in a state of auto-intoxication.
We are on safe ground only so long as we follow the teachings of the law of uniformity. The battle over the theory of the permanency of the Earth's greater features has been fought and won by Americans long ago.
"15 years later, a battle erupted which was the field of admirals and generals, not geologists and geophysicists. Engaging in anti-submarine and mine-sweeping operations, British and American scientists felt a tedium after their initial success in deploying their weapons of destruction. After the Battle of the Atlantic, scientists turned to modifying the electronics of war into instruments of research. Others acquired another skill. Before the war, science was considered a hobby by those outside the profession. Because of their contribution to the war effort, scientists acquired a new prestige. They learned how to lobby for money with an intensity to match their newly acquired esteem. Only when scientists turned their backs on the comforts of libraries and boarded ships with advanced funding and tools would the oceans unlock the secret of the continents. During the 50s, geophysicists conducted extensive ocean bottom profiling. If the oceans were permanent features, the sediment accumulated from continental erosion over 4 billion years should be about 4 miles thick. The echo-sounding profiles beyond the continental slopes reflected an average thickness of only several hundred feet. There was yet another surprise. Expecting to dredge up ancient Precambrian rocks, the drill cores consistently sampled rock less than 200 million years old. The ocean basins were youthful, less than 1/20th the age of the continents. Proceeding to map the ocean floors, scientists discovered a mid-oceanic ridge system that traced its way for 40,000 miles through the oceans of the world. This ridge system is associated with volcanic and quake activity. During this same period of research, scientists were engaged in paleomagnetic surveys, magnetic mapping of the Earth's surface. The magnetic data presented scientists with puzzling irregularities, or anomalies. In this strip pattern in the North Pacific, the dark area represents rock magnetized in the present direction of the North Pole. In the light areas, the rock is reversely magnetized. That is, the North Pole is located where the South Pole presently is. The results of all this research instilled a mood of unease and tension in the earth sciences. By the end of the 50s, the rigid Earth advocates were playing a wait-and-see game. Yet any geologist who was willing to revive Wegener's view did so at the peril of his reputation or at the risk of dismissal from his faculty. The 60s commenced as a decade of synthesis. A series of bold, brilliant papers are presented by geologists who had seen, in a flash of insight, connections between all the unrelated data collected in the 50s. Boos were heard at conferences when they presented their papers. The late Harry Hess of Princeton makes the first notable association between two sets of discoveries: the Midoceanic Ridge system and its volcanic activity. It occurs to him why the ocean basins are so young. They are constantly renewing themselves. Rising from the hot limbs of the mantle, lava is deposited at the surface, and spreading laterally, the seafloor then acts like a conveyor belt.
Yes, the concept was first...
Frederick Vine explains his discovery: a connection between those magnetic reversals and Hess's conveyor belt, which determines the speed of seafloor spreading.
Oceanic crust, that seafloor is continuously being created at mid-ocean ridge crests, such as the crest of the Mid-Atlantic Ridge here in the South Atlantic. It is generated above an upwelling in the mantle and spreads laterally away from the crests, thereby separating, drifting the continents apart as though they were on a conveyor belt of upper mantle material. So one might represent this, therefore, by a simple model such as this, illustrating the way in which the conveyor belt of oceanic crust and upper mantle material flows out from this central crack in the Earth's crust. Well, now, in 1963, Drum Matthews and myself, then at Cambridge, added the simple rider to this, and in effect converted his conveyor belt of oceanic crust into a tape recorder. We suggested that as new crust is formed, solidifies at a ridge crest, frozen into it will be the current direction of the Earth's magnetic field. This will be subsequently moved aside as newer material comes in. And in this way, successive avenues of crust, normally and reversely magnetized, will be built up, paralleling the ridge crest and symmetrically disposed about it. And indeed, going back to the anomaly map, the very detailed contour map of Rafa Mason for this area of the Northeast Pacific, and after peering at it for some time, we could see that indeed there is a remarkable symmetry of the magnetic anomalies about the crest of this so-called Juan de Fuca ridge in this area, and they do indeed reproduce all the details of the reversal timescale in remarkable detail. So to summarize this then, we drew up this new colored summary map, which emphasizes this symmetry about the ridge crests in a truly remarkable way. It's incredible to think that it had been in the literature for 4 or 5 years. In '63, it was very frustrating because I had this idea and one realized that if it was true, you know, the implications were enormous, that the ocean basins were young, ephemeral features, that all the oceanic crust, all the deep ocean basins that we see today were generated, say, within the past 200 million years of geologic time, less than 5% of the whole of geologic time.
But what of the earthquake activity associated with the ridge system? Tuzo Wilson provides the answer to the last part of the puzzle.
I remember being told as a student that the St. Andreas Fault had earthquakes along it, and they continued out to sea for some distance and then stopped abruptly. So there was a problem as to how a fault with large movement, which the Californians had suggested amounted over the many years to many miles of movement in this sort of fashion, could have motion like that which would stop suddenly somewhere out in the Pacific Ocean. And the idea occurred that perhaps something was going on as you can see on this piece of paper. And you see the spreading is taking place along here, where the material comes up to the surface. And as the material comes up, it allows sliding to take place along this line here. See, spreading here, sliding here. So the Pacific plate is bounded by the East Pacific rise, which is spreading, by sliding along the St. Andreas Fault, by another little bit of spreading off the coast of British Columbia and the state of Washington, by sliding off British Columbia, and then by subduction zones where the Pacific floor goes down under Alaska and Japan. And North America is part of another plate. So this was the origin of the idea of the transformed fault. And the continents are not being carried round as ships that are driving themselves, but are drifting around on the surface of these huge plates as rafts. And the Earth's surface is divided by these active zones where earthquakes and volcanoes occur into a number of separate rigid plates.
A little more mopping up with the aid of a computer, and the ancient annals of drift are recreated. Scientist Warren Kerry, who first proposed using the edge of the continental shelves to make the fit more accurate, testified, "I have even returned to Wegener's Pangea." And so had they all by the end of the 60s.
But a lot of people aren't happy about it because they weren't brought up with it. It's like asking a middle-aged man to change his religion, and they don't really like it. They would be delighted to see something happen that would destroy it all and go back to fixed continents.
There is a final irony. The Earth scientists still do not know what the driving mechanism is that propels the plates on which the continents ride. In Wegener's time, he was rejected because the forces he tentatively suggested were insufficient.
The Newton of drift theory has not yet appeared. His absence need cause no anxiety. The theory is still young. It is probable, at any rate, that the complete solution of the problem of driving forces will still be a long time coming. It is only by combining the information furnished by all the earth sciences that we can hope to determine the truth. This conviction gave me the stimulus to continue at times when my spirits failed me.
In 1930, Alfred Wegener died after setting out on skis over the polar ice of Greenland. When his body was found a year later, he did not appear to have died from either cold or hunger, but rather from exhaustion.
The film you've just seen depicts very clearly the very important role that Alfred Wegener had in the development of the theory of continental drift in the early part of this century. The theory of continental drift is now part of the history of geology insofar as it's been superseded by plate tectonics. Continental drift really treated only the continents as pieces of a jigsaw puzzle, but now plate tectonics treats the whole of the Earth's crust, the oceans, and the continents as pieces of a jigsaw puzzle. So the program today, looking at continental drift, is in a sense a flashback to part of the development of a current theory. One of the important events of the 1960s, which stimulated again attention to continental drift, was a meeting in London. I was fortunate enough to be a graduate student in London in 1964 when the meeting was held at the Royal Society, and the result of that meeting was this volume, a volume of papers by those who were adherents of the theory of continental drift, and also some by those who weren't, and particularly some quite vigorous discussion by those who were in favor of the stability and the permanence of the continents and the oceans at that time. This is one of the maps that was produced showing the fitting of the continents, a map produced by some Cambridge geologists. It's interesting to reflect on the tremendous change that's taken place in geology in the last 11 years. That map, which was produced by the Cambridge geologists, was a map of the fitting of the continents, particularly of South America and of Africa. It wasn't the first time that an attempt had been made to match those two continents. It was first suggested by Bacon in the 1600s and was repeated again in the 19th century by Antonio Schneider, who produced some geological evidence, the matching of fossils across these two continents. In fact, plants from the Pennsylvanian system. But unfortunately, this was the only scientific argument which Schneider put forward in support of his matching of the continents. He felt that the split had taken place during the time of Noah's flood, and this mixture of geology and theology didn't win him many supporters in the scientific world. Even Wegener, 50 years later, who was the first, and this was Wegener's great contribution, the first to marshal scientific arguments from many areas, from climatology and paleontology and geology, the matching of strata from continent to continent, even then Wegener had a hard time because he was unable to propose a mechanism. One of the things that Wegener was able to do was to produce a pretty good match of the continents. But the match which was produced in the 1960s was a computer match and was very much more accurate. It wasn't just based on eye, although the eye is a very good instrument for making comparisons of this kind. The computer was able to fit these two continents together with an accuracy of 99%. The average overlap, or the average gap, was about 90 kilometers, which isn't very much when you consider the size of these two continents. Now, you remember from earlier units that the edge of the continent and the edge that was used to match these two continents is not the coastline. The coastlines are marked here in black. The edge of the continent was taken by these Cambridge geologists as the 500 fathom line. In other words, 3,000 feet or 1,000 meters. And that was taken as a true edge of the continent. There are some areas of overlap and some gaps, as I mentioned. One of the areas of overlap is in fact up here. And that's where the Niger River flows into the South Atlantic at about this point. And the Niger River has built itself a delta of sand and mud, which has crossed the continental shelf, which is very narrow there, and built out and produced a protuberance, or a wart, if you like, on the 3,000-foot line, on the 500-fathom line that was used to match the continents. And it's for that reason that this overlap is here. Some of these small gaps can also be filled, or if not filled, at least made a little narrower, by looking around for islands, very small islands of continental rock, of granitic rock, which are now in the ocean, the South Atlantic, which divides these two continents. Now, one of the people attending that conference, a gentleman called Hurley, a geologist called Hurley from America, from, I think, the Massachusetts Institute of Technology, in fact, went back to his laboratory and reasoned quite obviously that if these two continents fit that well, then the geology ought to match from one to the other. The rocks ought to be identical, and they ought to fit together like the pattern on a jigsaw puzzle, or like the newsprint that you saw being torn in the film. And the particular rocks that he looked at, that Hurley looked at, were cratons, areas of very, very old rock, areas of rock 2,000 million years old and older. There's an area of that kind in Brazil, and one can see the perimeter of that area. Rocks 2,000 million years old, surrounded by other rocks 600 million years old. Hurley found similar cratons in Africa. In particular, he found one here, and there nearly all of the perimeter of that body of old rock was visible, but it came to an end at the coastline of Africa. So Hurley reasoned that if Africa and South America were once joined, it ought to be possible to find the continuation of that craton in South America. So he went over, and in fact, right here is a tiny little area of very, very old rock, 2,000 million year old rock, surrounded by 600 million year old rock, just as on the opposite coast. He tested this again with another craton. This time, again, the main body of the craton was in Africa, but a small part of it was once again traceable in South America. And from that kind of geological evidence, the kind of matching of the geological strata, ages of rock and kind of rock across the coastlines, came the conviction that fitting together the continents, like pieces of a jigsaw puzzle, was a very good way to get some idea of the way the continents might have once been joined. And it was as a result of that that further continents, in this case here, India and Antarctica, let's fit that a little better, and Australia, we have to move our continents a little here. Not quite as easily done as the computer did it, but nevertheless, computer fits of the other continents in the southern hemisphere, of Antarctica, Australia, and India, produced not too bad a pattern, particularly not too bad when you remember that islands like Madagascar would fill up this hole rather nicely, and the Seychelles are also islands of continental crust which fill up some of these gaps. This major gap here, which was a source of some concern and would be, I'm sure, to you looking at it, that's a very obvious gap. That gap is produced because the deformation of this part of Antarctica is quite recent and was probably produced after the continents broke away, and therefore the shape at the time that the continents were joined may well have been much more similar to the shape that's necessary to match this coastline. So that's a bit of deformation after the movement away of the continents. And similarly, one can explain some others of these small gaps down here. Now, not to be outdone by the geologists of the southern hemisphere, the geologists of the northern hemisphere also had a shot at fitting together their continents. Let's take these off and put the northern hemisphere continents together. Europe, but cut at the Urals, and North America. Where are we? And Baffin. Where are we? Good fits were obtained for the northern continents, North America, Greenland, and Europe. And once again, the geology matched across the coastlines, or matched across the outlines of the continents. Once again, these outlines drawn at the 500-fathom contour. There's a mountain belt that we know in the eastern seaboard of North America as the Appalachians, which runs over into Britain, Scotland, Norway, and touches the coast of Greenland. A continuous mountain belt right across all three pieces of this northern part of the jigsaw puzzle. Now, apart from the matching of the kind of strata, much of the evidence for the former union of the continents was paleontological. And one of the, was based on fossils. And one of the main participants in the debate about continental drift, one of the main authorities on the use of fossils in matching the continents is Dr. Karl Burt, who describes in this next piece of film his interest in the problem of continental drift and the union of the continents, or the evidence for the union of the continents based on fossils.
For the last 10 or 20 years, a great deal of evidence, physical evidence particularly, has been accumulated to support the theory of continental drift. The theory that the continents, as we now know them, have drifted to their present positions from original positions which were far different. Now, any theory to be viable must satisfy all aspects of the theory. And for many years, quite a few years, a good many paleontologists, people who study fossils, were not convinced by continental drift because they felt that it didn't explain the distributions of fossils any more than the idea of fixed continents. And I certainly felt that way for a long time. But as the evidence accumulated, there seemed to be more and more reason to believe in continental drift. There was a problem, though. If you can picture in your mind's eye the present arrangement of continents, you remember that there is a connection, a possible connection between Asia and North America in the Bering region. There's the Isthmus of Panama, and of course that connects all of those continents, and Australia is more or less connected. That is, there are shallow waters between Australia and Asia, and so it was possible to think or to postulate that animals got from one continent to another, animals of the past, by these bridges. And it's a long way around, that's true. But when geological time is taken into account, that long way around isn't particularly crucial, because if an animal spreads its range by a factor of, say, half a mile a year, in 20,000 years it will spread across 10,000 miles, and that's almost nothing in geological time. But Antarctica, it seemed to me, was a crucial key in this whole problem, because here was a completely isolated continent. Now, I had hoped for many years that perhaps fossils would be found on Antarctica, that is, fossils of land-living animals. If so, it seemed to me that would really clinch the paleontological evidence for continental drift. Well, in 1967, in December, a New Zealand geologist named Peter Barrett found this little piece of bone, which just happened to come to me for identification. This happens to be a piece of a lower jaw of a big amphibian that lived in lower Triassic times. And here was a first clue that there might be fossils on Antarctica that would have a bearing upon the position of that continent in lower Triassic times. On the basis of this bone, an expedition was organized to go to Antarctica to look primarily for fossils, because this bone had been found incidentally by a geologist who was working on other problems. Well, it so happened that I went to Antarctica with several colleagues, and we started collecting fossils. And we found various pieces of bone almost immediately. Bones like this, bones like this. This happens to be a piece of a pelvis. But I wasn't able to completely identify these because they were not the crucial parts of the animal. But on December 4th, 1969, a date that I remember very well, this piece of bone was found. Now this happens to be a piece of a little skull, and here is a skull. Now if you look closely, I think you can see that this corresponds with this part of the skull. Here's this portion of the bone known as the maxilla. Here's a tooth. Here's a tooth. Now this is the skull of a reptile, a fossil reptile known as a dicynodont, found in South Africa. This particular reptile is called Lystrosaurus. And here, for the first time, we had an indication that Lystrosaurus lived in Antarctica. I think the correspondence there is very close. So that was really the beginning of our good hard evidence as to the nature of the fossils in Antarctica. Well, subsequently, a lot of things were found. For example, here are the bones of a large Lystrosaurus, a shoulder blade, a leg bone, piece of ribs, and foot bones that were found in Antarctica. And here is a specimen which it may be a little difficult to see. Nevertheless, this is a crucial specimen because here is a skull cut right down the middle by processes of erosion of a Lystrosaurus of about this size. You see here, here's a tusk, here's the position of the eye, here's the back of the skull, here's the bottom, here's the top, and those correspond like that. So, to make a long story short, we found a great deal of material representing Lystrosaurus in Antarctica. Now, Lystrosaurus is a characteristic fossil of Lower Triassic age found in South Africa, found also in India, found also in eastern China, and it lives along with various other reptiles that were contemporaneous with it. For example, here is a skull of a little reptile known as Procolophon from South Africa. In Antarctica, we found a skull of Procolophon, and I think, can you see those? I think it's quite obvious that those are very similar indeed. This skull has been smashed down. If it weren't smashed, it would be very close to the other one. We found a whole skeleton of this, and indeed we were able to reconstruct the skeleton of this little reptile from Antarctica, which can be seen in this drawing, and a skeleton from Africa seen in that drawing. And you see there's the evidence of animals that were almost the same living in Africa and Antarctica. Now, animals like that were certainly land-living animals. See the feet? And they couldn't swim across great expanses of ocean. So I think this is good evidence that Antarctica was closely connected to Africa, and indeed that these animals represent individuals living in a single range, a range comparable, say, to eastern North America in aerial extent, which subsequently has become split apart by the drifting of Antarctica and Africa away each from the other. So those are members of the Lystrosaurus fauna, as we call it, and there are various other reptiles also belonging to this association of animals. But the characteristic thing was Lystrosaurus, as shown by these bones and as shown by this restoration of Lystrosaurus. This shows what the animal looked like. And I think here again, you can see that here is an animal that certainly wasn't a swimming animal, although we have reason to think that it lived along the edges of rivers and streams. It was a very strange kind of a reptile. It had this sort of a beak-like front of the skull. It lived upon plants. The evidence is pretty good for that. And these animals are found by the thousands in South Africa. As I say, they're found in India, and we find abundant remains of them in Antarctica. So the discovery of all of this material certainly turned me around completely. I was, as a matter of fact, pretty well convinced of continental drift before we found these. But this, I think, really clinched the matter, because here were animals that were obviously land-living forms. They had to go from Antarctica to Africa to India to China, across dry land connections, and I think this is good paleontological evidence that fits right in with the geological evidence to show that these continents were once part of a great supercontinent in the southern hemisphere called Gondwanaland. And I think this evidence from Antarctica is going to be very interesting as it is developed in the future. We've made 2 trips to Antarctica and have just merely scratched the surface of a large continent, a continent half again as big as the United States in extent, and there's a great deal of material of this type to be found in Antarctica, and I think more material and better material will be forthcoming in the future, and I think other types of land-living animals will be found there also.
Since Dr. Karl Burt was in the Antarctic in the late 1960s, not a great deal more fossil evidence has turned up. There are obvious problems because of the climate and the amount of the continent that's covered by ice. And even the rock which is exposed is not the kind in which fossils are commonly found. Most of it is metamorphic and igneous, and there's not very much sedimentary rock exposed. As Dr. Karl Burt pointed out, it's very important to choose the right kind of fossil when you're matching continents, trying to establish that they were once together and that the fossils were once part of one community. It isn't any good picking fossils which were able to swim across large expanses of ocean. This Mesosaurus was one that, like the Lystrosaurus, is thought to have lived in swampy areas and was quite incapable of crossing a wide ocean. And therefore the fact that it's found in many of the southern continents is a good indication of their former union. Another fossil that's been used for matching South America and Africa are the so-called ostracods. These are little shelled animals that live in swamps, very, very small, rather like shrimps. And they are only found in this area and this area, and we know from their present-day relatives that the larvae become sterile if they're exposed to seawater. So there's no possibility of the ostracods having crossed from this continent to this continent across an open ocean. The continents must, at the time of these ostracods, have been together. And the dating of the rocks in which those ostracods are found is quite interesting. They're about 100 million years old, perhaps a little bit older than that, 110, maybe 120. And in rocks that are younger than that, we don't find the same correspondence of fossils from South America to Africa. It seems that these ostracods were the last to be shared by these 2 continents, and it gives us a date for the breakup of this grouping of continents, Gondwanaland, as it's called. It seems that South America began to move away from Africa about 100 million years ago. Before that, India had already begun to move and eventually collided with Asia. Antarctica and Australia began to move as a unit, probably just a little before the South Atlantic began to open up. So fossils can also give us an indication of the time at which the continents began to move apart. Now, there's other evidence for the former union of these continents in rocks that are about 380 million years old, and that lies in the distribution of the traces of glaciation, an ice age in these continents about 450 million years ago. These colored pieces representing the area in which we find traces of glaciation in 450 million-year-old rocks. Now, of course, as the continents are presently situated, with India farther up here and these 2 separated, Antarctica down here, Australia over there, it makes no sense at all. But if we put them back together again and close up according to the geometry of the continents, then this area, and we think that Antarctica has the same traces of glaciation, but of course it's much hidden by ice and we don't have very much evidence. This describes a very nice kind of polar glacial ice cap about 450 million years ago. Also evidence for the existence of this grouping of continents at a certain time. We think, in fact, that this grouping, Gondwana land, formed about 500 million years ago and began to split about 180 million years ago, and finally split into all of its fragments about 100 million years ago. Now, there's also good evidence from paleomagnetism, which perhaps you remember from oceans, that the continents have moved. Let's just deal with two of them and look how that indicates that the continents may once have been united. You remember that when igneous rocks cool, they assume, as the iron minerals such as magnetite cool through the so-called Curie point at about 580 degrees centigrade, they assume the direction of the Earth's magnetic field. We talked about this in oceans. And when the continents were united, we can assume that they would, all the igneous rocks cooling at a particular time would have the same direction frozen into them. They would point to the same North Pole. If we collect rocks of identical age today from Africa and South America, we find that rocks of the same age point to quite different places, very, very separate positions for the North Pole of, let's say, 400 million years ago. But if we put them together again, according to their geometrical fit, to their jigsaw fit, we find that they point to the same North Pole. And this can be done with all of the southern continents and also with the northern continents. And it was this evidence from paleomagnetism that finally clinched the theory of continental drift.
Stay tuned for a short public membership break. You can show your support for TV Ontario programming by calling in a financial donation at 483-5555 from